All right, so what we're going to talk about today are graphing trig functions. Specifically, we'll talk about graphing sine and cosine today. We'll talk about graphing the other trig functions in a future section. Today we'll focus on sine and cosine. And just to give you a little preview of how this lesson is going to work, we're going to go through the next several pages. And this first page here is a reference page which is going to end up setting up what sine and cosine look like. Okay, we'll kind of get the general idea behind why those shapes, why these two graphs have those two shapes. The one on the top here is sine, the one on the bottom is cosine. We'll relate that back to the unit circle and try to understand how we can remember those shapes. And then what we're going to do is we're going to plot these transformations of these two graphs, I should say, just like we've done transformations for every other function we've graphed. The difference is with trig functions is they can get increasingly complicated. And so just looking ahead on the next couple of pages, once we have a good idea from this page about what sine and cosine look like, we will add some complexity to them by adding some numbers and multiplying. Okay, this is the next page. On the following page, we will then add another complexity by adding a k inside. And then finally on the last page, we'll add a third complexity, which are shifts. And so notice that on each subsequent page, we add another level of complexity to the problem. But just know that we're just doing transformations like we've done transformations of everything else, okay? And again, with the first form, we'll just talk about vertical and horizontal shifts. Vertical shifts and stretching. On the second form, it'll be, we'll add the k in the middle, which is going to be a horizontal stretch. And on the third, we will add the b inside, which will be a horizontal shift. Okay, so we'll add increasing complexity after we have a good understanding of what each function looks like. So let's start by taking a look at what each function looks like. So we have this page, and the first thing that we're being told in this page is that the functions sine and cosine have period 2 pi. And so that's what's being said in these two equations. It's saying that when you plug in a number into sine, and you add 2 pi to that number, it's the same as just plugging that normal number in. Same thing with cosine. Okay? So the big takeaway from this is that sine and cosine have a period of 2 pi. And just looking at these equations, what that means is that the graphs start to repeat themselves after 2 pi units, which is why the value at t is the same as the value at t plus 2 pi. All right, so let me write that down here and then say it one more time. So the period, the definition of a period, is how long it takes the graph to repeat itself. Oops, so how long it takes for the graph to repeat itself. And so we know that sine and cosine are based on the unit circle. We know that sine is the y value, are the y values on the unit circle, and cosine are the x values on the unit circle. And we know that those values, right here's the unit circle right here, I'm going to refer back to this. The values as we go around the unit circle repeat themselves every 2 pi units. And that's because the unit circle is 2 pi, the perimeter is 2 pi distance. And so every time we go around 2 pi units, we repeat the same exact values. And that's why these functions repeat themselves every 2 pi units. And so let me write that down. So since the unit circle has a circumference of 2 pi, the values, the x and y values on the unit circle, repeat themselves every 2 pi units. And specifically, maybe units isn't the best word. They're radians specifically. The unit are radians. So every 2 pi radians, as we go around this unit circle, we see that the values are going to repeat themselves. And so that's why these sine graphs and cosine graphs repeat themselves every 2 pi units. And as we just look down here at these two graphs here, we can see that we're showing one period right here. We're showing one period of the graph because the graph starts to repeat itself right here. See how this is the starting point and it comes back to that point right here, and then it repeats itself again after that point. And same thing with cosine. Okay, so just to be clear again, this is sine up top, This is cosine down here, and we can see that cosine again repeats itself every 2 pi units. And so just looking at these two graphs before we get any further, this is one period. One period's being marked out from 0 to 2 pi, okay? And then another period would be from 2 pi to 4 pi. This is another period, because this also repeats itself, and another period right here. Now, I'll come back to this in a second. Let's not get too far ahead of ourselves. Let's understand the shape of the graph and why the graph looks like that. And so again, we've got sine and cosine being shown down here at the bottom page, and here's kind of a zoom in on what they look like. But let's take a zoom out on just sine and focus on sine and understand why sine looks like this. So let's notice some characteristics about it. So we know sine are based on the y values, right? Let me just write that down. When we want sine of t, this is from a previous class, we think about the y value on the unit circle. That's a key. It's a key to us understanding a lot of trig is relating everything back to the unit circle. And if we're talking about sine, that means we're talking about the y values on the unit circle. So let's look at this unit circle. And if we're talking about the y values, notice that if we start at 0, the y values increase to 1. Right? This first piece of the graph where the y values increase to 1, I'm just going to kind of highlight it here. Yours may not be in color, but mine, I'm going to try to make in color here. Let's make these lines red. These lines are getting taller because the y values are getting closer to 1. That's this graph. This is sine. That's this part of this graph. See how these lines are the same? They're the same height. So the y values start at 0 because they start at 0 over here. And as the y values increase here, the graph of sine increases. But then at this point, the y values start to decrease. And so that's this part of this, on the graph on the right, where these y values start to decrease. And so I'm going to just highlight these in blue, just to be clear about that. The y values then start to go down on the unit circle, and so the graph of sine starts to go down. Okay? And it hit its peak at 1. Of course, we know the max is at 1, right? So the y values went up to 1, and then they went back down to 0. And that's why this graph of sine goes up to 1, and then back down to 0. And then, if we're thinking about the y values still, the y values then go negative to -1, right? This is -1 down here. And then the y values increase back to 0. And so that's this piece of this graph, where the y values go down to -1, and then increase back to 0. And so let me just highlight that again on this. That would be like this line. These lines are now going negative, and so these lines are going negative to -1. And then these lines go positive. I'll do it with this. These lines go back from -1 to 0, and so that's why this piece of the graph goes from -1 back to 0. Now, let's notice some of the characteristics. Oh, and so let me just say that this graph here is just showing one period of pi, right? So one period of pi starts at 0 and it goes, one period of sine starts at 0 and goes to 2 pi. So this is one period of sine of t. Okay, and we can see that it has its 0 at pi, and we know that the point's pi right there because the 0 is at pi right here. The y value is 0. And so if this is just one period between my hands, it's showing us just this first period right down here. So I'm connecting the dots back to this bottom picture of sine, and we can see that what's in between my hands right here on the bottom, let's focus down on this graph. What's in between my hands down in this bottom graph is what's being shown up on this graph. Okay, so just know that this graph up here keeps going in both directions. It keeps going to the left and to the right, as is shown right here. Okay, so the periods continue in both directions. And so this graph keeps going. It goes out to the right and to the left. It just keeps going out, out, out. And you can see that we have a period here, we'll have a period here, we'll have another period here, we'll have a period here, and it just keeps repeating itself over and over and over again. And just as a reminder, just like, you might be thinking, like, why the heck do we care about this function anyway? Why do we want a graph that just repeats over and over? We use graphs like this to model phenomena that repeat. For example, the rising and the setting of the sun can be modeled using trig functions like sine and cosine, right? You can imagine this is the sun going up in our skies here in Fitchburg, and then it goes down, and it goes behind the other side of the Earth, right? And now it's going and it's rising on the other side of the Earth, and it's setting, and then it rises again on our side, and then it sets, and it rises on their side, and it sets. And that process repeats itself. And so we can use functions like this to model those behaviors. And those behaviors and those types of phenomena happen a lot. Another example that I may have mentioned before is population dynamics. So interactions between foxes and, say, foxes and rabbits is a really good one. You can model that with sine and cosine. So follow my pen with this. Let's pretend that this is a fox population on the top, and this is a rabbit population on the bottom. So you can see the fox has a low population, the rabbit has a high population. Since there's a lot of rabbits down here, the foxes can eat, and the foxes' population increases. As the population of the foxes increase, they eat all the rabbits and they decrease, right? And then as soon as there's not enough food left, the population of foxes decreases. But when the population of foxes decrease, there's no predators, and the population of rabbits increases. And so the dynamics, the interplay between increasing and decreasing, we can see in populations in the real world as well. Okay, so just trying to motivate like why we care about these graphs and what kind of phenomena we might think about modeling with these. Maybe you can think of one yourself. I encourage you to try to think about something in your own life that kind of repeats itself over and over, and what could we use to model that, what trig function could we use to model that with. So we talked about sine. I'll just say again, sine are the y values on the unit circle. The y values increase, decrease, become negative, and then go back to 0. And this is what is kind of a close-up of what's going on in the sine graph. So this is one period of sine you can see that's being graphed here. And you can see that it's got all the pi markers on it from 0 to 2 pi. Right, so pi over 6, pi over 3, pi over 2. These increments, these increasing increments, are the increasing increments around the unit circle that we've been practicing. Let's take a second to focus on cosine too. So if we're talking about the cosine graph and we're relating it back to the unit circle, so this is showing cosine down here. Okay, we've got cosine on the bottom. And they look very, very similar, but they're slightly different. And that's because cosine depends on the x values. Right? Cosine are the x values on the unit circle. So let me just write that down here. When we want a cosine value, we think about the x value on the unit circle. And so if we look at this unit circle and we think about the x values, we start here and x is 1. And then as we go around the unit circle, the x values get closer to 0 until there's 0 right here. And then they become negative, right? And then the x values go back to 0. And then they become negative, and then become positive back to 1. And that's what's going on when we look at this graph, right? Let me trace it out with both. If we start here on the unit circle, we're starting right here with this graph down here. And as the x values start at 1 and go down to 0. So they start at 1 on this graph and they go down to 0. And then the x values on the top, on the unit circle here, become negative to negative 1. And you can see down here, they become negative to negative 1 at pi. And then as we move to over here from pi to 3 pi over 2, the x values go back to 0. And so down here, they go back to 0. And then the x values on the top here go back to 1. And you can see it on the bottom graph, they go back to 1. And so this graph, if this is one period of sine, this is one period of cosine. And you can see that they don't look the same like this. I know when you kind of compare these two graphs, they look very similar because they both have a wavy pattern. But when we focus on just one period, which is what's being shown here, they're opposites of each other in some sense, right? When sine's 0, cosine's 1. When cosine is 0, sine is 1. And so they're translations of each other. They're shifts of each other. If we shifted sine over, it would look like cosine. Or if we shifted cosine over, it would look like sine. Right? Because when we think about going around the unit circle, the x and the y values are all the same. They're just in different order. They're just shifts of each other. Okay? And so again, just like we see repeating periods of sine we have repeating periods of cosine. Here's one period of cosine between my two hands, right? So this period right here, that's one period. We've got another period on either side. This is one period over here, period. This is one period over here, right? You can see that the graph is repeating itself in each one of those pieces. And so we just see those repeating periods over and over.
So you know the building's going to lock at like 10:30 tonight?
Oh. And so in case it wasn't clear, what we want to do based on this page is we want to use these pictures as references as when we're doing transformations. And so I'm just going to write that down just to be very, very clear about that. We want to reference these pictures and all the information we just learned about them when we're doing transformations. So reference these when graphing transformations. Oops, graphing transformations of sine and cosine. And so with that in mind, since we want to reference things when we're graphing sine and cosine, let's write down a few of the characteristics of each graph. Because when we do transformations, if we move the graph up, we want to know where the new max and mins are. So we need to know where the old max and mins are, right? If we shift something to the right or to the left, we might want to know where the new intercepts are, and so we need to know where the old intercepts are. So let me just take a second. Let me see where I can squeeze this in. I'll try to squeeze it in right here. I'm going to squeeze in something here for sine, and then I'll write something for cosine down at the bottom here. Okay. So for one period of sine, we get the following. Notice that there's a min at 0, and there's a max at 1, right? That's because the smallest y value is 0. I'm sorry, let me start over. We get a min at -1, not 0. There's a min at -1 and a max at +1. That's because the smallest y value is -1 and the biggest y value is 1, right? And so for one period, we have a min/max at y equals ±1. All right? The min, right, so the -1 part, this low point on the graph, this low point, you can see that it occurs at 3 pi over 2. And that's because this point right here, where the -1 y value is at the point 3 pi over 2. And the max is up here at 1, and that occurs at pi over 2. And we can see that on this graph. So notice that the max is at pi over 2. Okay, so let me write that down. So the min is at t equals 3 pi over 2. And the max is at t equals pi over 2. Again, that's because that's where the min and the max y values are. Let's look at where the intercepts are. So the intercepts are here, the x-intercepts. The x-intercept is here, here, and here, right? It starts at 0, it comes back to 0, and then it comes back and hits 0 again. And it happens when all the y values are 0. So the y value of 0 is here, here. These are the two places where the y value is 0. And that's t equals 0, t equals pi, and t equals 2 pi. And so that's why we have a 0 at 0, we have a 0 at pi, and a 0 at 2 pi. Because again, the sine is the y value, and that's where those y values occur. And so the x-intercepts for sine are at t equals 0, t equals pi, and t equals 2 pi. Okay? And again, we want to know that information because when we shift it around, we'll shift the intercepts and or the maxes and mins. Okay, so we want to know where those are. Just going to pause it just 1 second here and make sure you're caught up with that. For one period of cosine, I'm going to write that down here. Okay, so we're going to write down that same information for cosine. So for one period of cosine, we see that the min, again, is at -1 and 1. Right, the min happens down here at -1, the max is at 1, and again, on the unit circle, that's because the biggest x value is right here at 1, that's t equals 0, and 2 pi, and the smallest x value is right here at -1, that happens at pi, right, and so we can see that happening here. At pi, we get the smallest x value, and then at 0 and 2 pi, we get the biggest x value. And so we have the same min and max at y equals plus or minus 1, but the locations are different. The min occurs at t equals pi, and the max occurs at t equals 0 and 2 pi. Again, just think about where the x values are on the unit circle. Cosine are the x values, and so when we're tracing out the x values on this thing, it's tracing out this cosine graph. The intercepts, we can see the intercepts occur right here and right here, so that are where the x values are 0, right? The x values are 0 on the unit circle at right here and right here, right? Those two places are the two places where the x value is 0. And that occurs at pi over 2 and 3 pi over 2 on the bottom. And so that's where the x-intercepts are for cosine. So the x-intercepts are at t equals pi over 2 and 3 pi over 2. Again, that's because that's where the x values are 0. So now what we're going to do is we're going to take these general shapes of sine and cosine and this information about where the mins and the maxes and the intercepts are, and we're going to do some transformations on them. And as I mentioned before, we're just going to make it sort of increasingly more complicated as we go, but you want to make sure you have this page on hand, right? You want to have this page on hand to reference. I'll be referencing this a little bit too. I'll be drawing kind of these pictures on the other page, and we'll transform them. So the first form we're going to look at is kind of the simplest form. And so you can see that we are not just taking sine and cosine, but we're multiplying them by a number, a, and we're adding a number on the outside. Okay, and so when we're thinking about looking at that, we can use the techniques found in section 2.5. And when I say section 2.5, I mean the transformation section. So what we're doing is we're thinking about these in terms of transformations, just like we thought about every other function with transformations. It's the same exact concepts. And so just like with the other concepts, you can see the c is adding a number outside the function, and so the c shifts the graph up and down. Because we're adding a number to the outside of the function. If the number is positive, it moves it up, and if the number is negative, it moves it down. And the a is multiplying the function by something. So notice how the a is on the outside of the function, and it's multiplying the function. And so the a is a stretch or a shrink. Right? If a is bigger than 1, it's going to be a stretch, and if a is less than 1, it'll be a shrink. So let me write that down. So the c shifts it up and down. The a is a stretch / shrink of the graph. And so if we happen to stretch or shrink it, we're going to end up changing the max or min. Right, so think about taking one of these graphs of sine or cosine. If we took them and we stretched them, so this is my stretching motion. If I stretch that, then these max and mins would be higher or lower. Or if we took that and we shrunk it down, right, the max and the mins would be smaller. And so when we do a stretch or a shrink, we need to change the intercepts. Okay, so a is a stretch or shrink of the graph. And what I'll say is, since sine and cosine have a max or min at plus or minus 1, when we stretch and or move the function up or down, we get a new max or min. So c plus A sine x and C plus A cosine x have max and mins at C plus or minus A. So this is the key relationship you want to think about. This is where the max or the mins occur. Okay, the C shifts the graph up or down, and then plus or minus A is the stretching part. And so we think about the new max or mins at whatever that value is. So let's look at this first one. 4 plus sine. So practically speaking, what we're doing is we're taking the sine graph and we're adding 4 to it. And so what that's doing is it's taking sine and it's moving it up 4. And so I'm thinking about this sine graph, right? This is sine, and I'm thinking about moving it up 4. And so I'm just going to sketch what that looks like on this graph, right? Normal sine has a max or a min at plus or minus 1. It starts at 0, it goes up to 1, comes back down to 0, goes back down like that, right? And the intercept is at pi, and 2 pi, and 0. And of course it goes in the other direction too. I won't draw the whole thing in detail, but it goes in both directions, right? So this is normally what sine looks like. And what we're doing is we're taking the sine graph and we're adding 4 to it. And so we're taking this and we're just shifting it up 4. And so our new graph is going to be that exact same graph but moved up 4. And the new max or min is going to be at C plus or minus A. So in this particular function, if we're looking at this form, C is 4 and A is 1. Right, so our new max and min are at C plus or minus A, which in this case is 4 plus or minus 1. So we get 3 and 5. So that's going to be our new max and min. So our new min is going to be a little bit higher at 3, and the new max is going to be up here at 5. The same graph, just shifted up like that. Okay? And so we go, try my best here, we go up, come back down to 3, back up that way. It's not the most pretty looking graph. And of course it goes in the other direction as well. This is what 4 plus sine would look like. And just like, just like the other sketches we do, I'm not looking for a beautiful graph. I'm not going to be able to draw a beautiful graph, and that's not the point. The point is that we know the shift, right? We have the correct shape, we have the correct shift, and we have the correct intercepts. And remember, since this old intercept was at 0, if we moved it up 4, this new intercept's now at 4. And you can just see there's not going to be any x-intercept. Let's take a look at the cosine one. So there's two things going on with this cosine graph, right? We've added 1 to the outside, and so that's going to shift it up 1, right? So this 1 is going to shift the graph up 1. But the negative sign on the outside, that's multiplying the cosine by -1. And if you remember from the transformation section, what that does is that flips it upside down. And so we're going to add 1 to cosine and flip it. Or flip it first and then add 1. And so let's do that in 2 steps. I'm going to draw 2 small graphs over here of cosine just to be clear about what it might look like. And so we're thinking about cosine, right? So cosine is now this one. Remember, cosine starts at 1. It goes down to 0 at pi over 2. It has a negative value. It has its min at -1 at pi, and then goes back up to 1 by 2 pi. And so I'm just going to sketch that graph right here so we can imagine transforming it. So cosine usually looks like this. 1 period of cosine, of course. So that's normal cosine, right, just from the other page. And so if we flipped it upside down, we imagine taking that graph and just flipping it. And so it's going to have the same max and min, it's just going to be upside down. So let's draw that graph. If we flip this graph upside down, it would look just like that, but upside down. So it would look like this instead. All right, so this is minus cosine. And so that's cosine. We've got minus cosine right there. And then we're adding 1 to it. And so it's going to be this graph that we just drew down here, but shifted up 1. Right? And so our new max and min, I mean, just looking at this, if we shift everything up 1, this becomes a 2, and this goes to 0. And we can use this formula to do it too. We have the new max and min at c plus or minus a. C in this formula is 1, A is minus 1, so we get 1 plus or minus minus 1. So that'll be 1 plus minus 1, which is 0. And then we'll get 1 minus minus 1, which is a plus, which is 2. And so here are our new max and min at 0 and 2. So our min will be down here at 0. Our max will be up here at 2. This is 2 right here. And it'll look like this because it's flipped upside down. So it'll do something like this. And it keeps going, of course, in both directions. Right. It's got its midpoint at pi, and I'll just draw one period going the other way as well. It goes like this. Again, it keeps going that way as well. Here's minus 2 pi. All right, so we did it in 2 steps. We flipped it. We started with cosine. We flipped it, and then we moved it up 1 because of this, and we figured out where the new max and min was at c plus or minus a. All right, let's take a look at the next one. So this next one is a transformation of sine, and you can see we're not adding anything to it, right? In these two, we were adding a number to it, and so we're not adding anything to this one. We're only stretching it, right? And so we're just taking sine and we're vertically stretching it by a factor of 2. We're multiplying all the y values by 2 when we do that. And so this is a vertical stretch of 2. And so we're thinking about just taking our normal sine graph and stretching it by 2. So we're going to take our normal sine graph, we're going to take this normal graph and just stretch it and make it twice as tall in both directions. And so you can see the new max and min is going to be at plus or minus 2 instead, because everything's going to be doubled. And if you weren't sure about that, we can just use this formula, right? The new max and min is going to be at c plus or minus a. And so our max slash min in this formula, or in this equation, 2 sine x, c plus or minus a equals 0 plus or minus 2, right? C is 0, a is 2, and so this is just plus or minus 2. And so you can see, right, the max and the min just doubled. It used to be a plus or minus 1, and now it's a plus or minus 2. And so again, we'll draw this exact same graph of sine, starting here at 0, except instead of going up to 1, we're going to go up to 2. We'll come back down to pi at the same spot, and then instead of going down to negative 1, we'll go down to negative 2, and we'll come back up. Okay, so it'll just be twice as tall. And it'll cross, it's still going to cross at pi, still going to come back up for 2 pi. Just a much stretchier version. And I really only ever want to see one period of this stuff. One period's all you really need. But I usually like to just draw 2, just to be clear that this graph is, it continues in all directions, right? It continues in both directions. We really only care about one period, which is right here. But there's another period. You could have drawn that period if you wanted to. We usually focus on the one closest to the 0 on the right, but any period will do. Let me let you think about that one for just a second here. And really, at this point, I would recommend pausing the video and trying this next one. Okay, we've got The 2 is raising the function, it's a vertical, a shift vertically up, and the minus 1/2 is going to flip the function and shrink it. And so we want to think about how to do that. I would recommend pausing the video right now, trying it, at least thinking about it, at least try to write down what the max and the min are, right? The max and the min are at C plus or minus A. At least try to do that. And then hit play and see how it goes. All right, I'll pause this for a second, let you do that. I hope you took the time and gave that a try. So again, this 2 is taking the graph and shifting it up 2. And the minus 1/2 is doing 2 things. The minus sign is flipping it upside down. And the 1/2 is shrinking it by a factor of 1/2. And again, you can see we're looking at a cosine function. So we're thinking about taking the cosine function, moving it up 2, but also flipping it and shrinking it. Okay, so we're going to do that with this cosine function. And I'm going to draw, again, some mini graphs over here on the right. Well, actually, I'm just going to refer back to these ones, right? So we're taking the cosine, and we're flipping it again. So we're going to have this same graph, but it's going to be flipped. So we'll have this kind of shape, except that this graph is going to be moved up 2 because of this 2, and it's going to be shrunk. It's going to be half as tall. So instead of going from minus 1 to 1, it would be going from 1/2 to positive 1/2 before we moved it up 2. Right? And so let's just write down what the min and the max are. The min and the max are going to be at C plus or minus A. You can see C is 2 and A is minus 1/2. And so this is going to be 2 plus or minus minus 1/2. And so that's going to be 1.5 and 2.5. Because the graph moved up. Right? And so our max, our new max and our min are going to be at 1.5 and 2.5 instead of 1 and minus 1. And it's going to look like this. It's going to be an upside down cosine that goes between those 2 points. We're still going to have the same max and the min though, right? So we're still going to have this is, think about this flipped upside down. We're still going to have a peak at pi, okay? And then the mins are still going to be at 0 and 2 pi. And so the peak is still going to be here at pi, and then we'll have the mins at 0 and 2 pi. So it's going to look something like this. Let's move this 2 pi over. That was a little far over there. And it keeps going in both directions. I'll just draw one more period going the other way as well, just to be clear. But that's what that might look like. Notice we've got our min and our max at 1.5 and 2.5. This peak is still at pi, right? Because we've got the upside down cosine shape right here, and that's what that one might look like. Now what we're going to do on the next page is just add a new step, add another little wrinkle into the equation here. And so this is the second form we're going to look at, right? Form 2. We've still got the C and the A, right? We've still got the C plus A there. But the new thing is we've got a K inside the function, right? The K is multiplying the X inside the function. And so if we think back to the transformation section, if we're given a function f of x, think about what is f of kx. Remember that? That's multiplying by a number inside the function. What that does is it horizontally shrinks or stretches. Okay, if the number is bigger than 1, if k is bigger than 1, it's a shrink, and if k is less than 1, it's a stretch. And so when we have something that looks like this, sine of kx or cosine of kx, it shrinks or stretches it. And so let's introduce a couple vocab words. The height of the graph we call the amplitude. And so that's how high it is, right? So the amplitude of this graph we can see here is what's between my two fingers. It's how high is the graph. The period, we already said, is how long it takes the function to repeat itself. Now, if we have a graph that looks something like this, c plus a sine of kx, like look at these down here, like this one, right? Our c in this one is 1, our a is 3, just to relate it back there, this is c, this is a, and that k would be pi in this example. If we have something in that form, what we want to do is we want to think about how, what interval should we graph this on? So explanation of form here. The a and the c do the same thing that we just saw on the previous page. So the a and the c act the same as what we just saw on the previous page, right? They move it up and down, or they stretch or shrink it, the graphs. The difference here is that the k is now taking the function and moving it in or out. Okay, and so before I write that down here, let's look at this graph. Let's look at this picture down here. Normal sine is the black line. So between my finger and my pen is sine, right? Starts at 0, has an intercept of pi, and then intercept of 2 pi. If we have 1/2, if we multiply by a 1/2 on the inside, notice how it's stretched it out. And so now the new intercepts are twice as big. Instead of being at pi, it's at 2 pi. And instead of being at 2 pi, this ends at 4 pi. If we multiply 1/3, it's stretched out by a factor of 3. Right? So this intercept at pi moved to 3 pi. This intercept at 2 pi moved to 6 pi. And so we can see here that multiplying by a number inside the function that's less than 1 is stretching out the function horizontally. If we multiply by a number bigger than 1, like this here, 2, it takes our original function and it shrunk it in by a factor of 2. It used to be out here at 0 and 2 pi, and it shrunk it in so that it's half as wide. It only goes from 0 to pi now. And so the a and the c do the same thing, but what the k does is it changes the period. The period on this original graph was 0 to 2 pi, the black line, right? If we look at the red line has period pi, because the graph would repeat itself after pi units. If we looked at the blue line has a period of 2 pi. And so what I want to say related to k is that k changes the period. So the difference here on this page is that the k determines the period, i.e., how often to repeat the graph. So on the last page, everything was from 0 to 2 pi, right? Everything on the last page, if I just flash it up here, all these things were from 0 to 2 pi. We had the same period for all of them. But now when we multiply by a number inside the function, we need to change the period. Okay, so on the last page, we always graphed on the same period, 0 to 2 pi. Now on this page, we want to graph on a different period. We want to graph from 0 to 2 pi divided by k, whatever k happens to be. Okay? And just to remind you, just looking at this formula, if k is a number that's bigger than 1, that this is going to be 0 to something that's less than 2 pi. Right? So if k is between 0 and 1, it's going to be a stretch horizontally. And if k is bigger than 1, it's going to be a shrink. Again, horizontally. And so we want to do the exact same thing we did in the last page, but we just want to graph on a different period. So let's look at this first example and see what I mean here. So we've got this function. The 1/2 is something from the previous page. The 1/2 is a shrink. Okay, the 1/2 is shrinking it. The 4 is a horizontal shrink I'm sorry, horizontal shrink, right? It's a shrink because k is bigger than 1. So this is my k, and this one is 4, and my a is 1/2. And my c, obviously, here is 0. There's no c. And so we're taking the cosine graph, we're shrinking it by 1/2, and then we are vertically, and then we're shrinking it by a factor of 4 horizontally. So let's figure out what the max and the mins are before we get started on this one. A is 1/2 in this, and C is 0, right? I just wrote that at the top here. And so that means, based on our last page, the max and the min is at 0 plus or minus 1/2, right? C plus or minus A. And so that's going to be plus or minus 1/2. And so the max is going to be up here at 1/2 before I do anything, and the min is going to be at minus 1/2. The k is changing the period, and what we just wrote down at the top here is we want to graph on this new period. This is kind of the big thing here. We now want to graph from 0 to 2 pi over k. And so our k here is 4, and so we want to graph on 0 to 2 pi over k. Let me change that, actually. I don't want to say graph on it. I mean, it's true, we do want to graph on that, but what I mean is the period has changed, and the period is now a different number. Zero to 2 pi over k. K is 4 here, right? And so we'll graph this on 0 to 2 pi over 4. Right? And 2 pi over 4 reduces to 0 to pi over 2. Right? 2 goes into 4 twice. And so this is our new period. And so we have a max or a min, but now horizontally, instead of going from 0 to 2 pi like we did on the last page, we're going to go to pi over 2, and that means halfway in between there is going to be pi over 4. Okay, and it's a cosine shape. And so we're going to use the cosine shape. We're going to use this shape here, except we've got a new max and a min. It's not at plus or minus 1 anymore, and we've got a new period length. It's not 0 to 2 pi anymore. Okay, we've got new things going on here. And so this would look something like this then. Okay? And the intercepts are going to be in between those two things, right? So halfway between pi over 4 and pi over 2 would be this intercept. Halfway between 0 and pi over 4 would be that intercept. So this is going to be this will be pi over 8. And then if we want to know what's halfway between there, we might think pi over 4 plus pi over 2 over 2. Let's find out what's halfway between those two things. And so if we add those two fractions together, we get 3 pi over 4 over 2. And so that's 3 pi over 8. So that's 3 pi over 8 right there. And again, it keeps going in both directions. So we've got this one that goes in the other direction as well, and it would keep going in both directions. But again, just to summarize how we did that, we looked and saw what C, A, and K were. We used C and A to figure out what the max and the min were. And then we used K to figure out what the period was. All right? And we know what the shape of cosine is, and so we just put all those things together to get that graph done. Okay, let's look at the next one. So I've already got my C, A, and K labeled, right? All right, C is 1, my A is negative 3, and my K in this problem is pi, right? The pi is the K in this problem. And so it's a sine problem, and you can see that because of this negative sign, this negative value right here, that's flipping it. This is going to flip sine over the x-axis. And so we're thinking about a flipped over sine. So we're thinking about this graph, but flipped. So instead of going up first and then going down, it's going to go down first and then go up, right? So just to be clear about that, just so we have it here in the back of our heads, instead of doing sine, which looks like that, we want to flip it. And so we're going to be thinking about doing this instead. Forget about that last part, right? This is minus sine. So we're starting with this kind of thing, and then we're going to stretch it, move it up, which is what the 1's doing, and then the pi is going to shrink it horizontally. But before we draw anything, let's figure out what the maxes and the mins are. Okay, so in this problem, our a is minus 3, and our c is 1, and so we use the max slash min formula. C plus or minus a, so 1 plus or minus negative 3. And so that's going to be 1 minus 3 is negative 2, and then 1 plus 3 is 4. So our max and our mins are at 2 and 4. So before I do anything, I'm sorry, minus 2 and 4. Our min's going to be down here maybe at minus 2, and our max will be up there at 4. Let's figure out the period. Our k in this case is pi. And so we have, we want to use the formula that I wrote down right here, that we want to graph from 0 to 2 pi over k. So if k is pi, those pi's will cancel, and we'll just go from 0 to 2. So let me write that down. K equals pi. So the period is from 0 to 2 pi over k, which in this case equals 0 to 2 pi over pi, which is 0 to 2. Right, the pi's cancel. So let me get that sketched out, and then maybe we'll think about the intercepts. So we've got our max and min at minus 2 and 4. We're going to have this shaped graph because we've got a flipped over cosine. And then we're going from 0 to 2. Oh, let me write that down. So we're going to have our max out here is going to be at 2, and halfway between it will be 1. And so the graph will look something like this. So and the y-intercept is going to be halfway between those two values. Halfway between those is at 1. And so the graph is going to look like this. And of course it'll keep going. And I'll just sketch out one from the left as well. We'll do a similar thing over there. Okay, great. So let me just write down how I got those intercepts, right? If the period is from 0 to 2 pi, and we look at sine, the intercept is in the middle of those two. If it's usually from 0 to 2 pi, the intercept's in the middle at pi. And so if this one goes from 0 to 2, then the intercept is going to be in the middle. Okay, so I got the 1 on the x-axis because it's the midpoint of the period. And then I got this y-intercept because, again, if we look at the y-intercept on sine usually, the y-intercept usually is at 0, which is halfway in between minus 1 and 1. See that? It's halfway in between my finger and my pen. And so if we know the max is at 4 and the min is at minus 2, then the intercept is going to be halfway in between them. And so that's where that one came from. The 1 on the y-axis is the midpoint of the max and min, minus 2 to 4. And so again, just to summarize, like we start by just analyzing the c, the a, the k, figuring out how that changes the max, the min, and the period, knowing the shape of it, of the function we're drawing a general sketch, and then thinking about what the intercepts are based on those changes. Something I forgot to mention as we were doing this is, I mentioned that the amplitude is the height of the graph, and I've talked about, how the period changes to 2 pi over k, but I forgot to mention that the amplitude of these things is whatever the absolute value of the number that's being multiplied on the outside is. And so on this first graph, since we're multiplying by a factor of 1/2, the amplitude of this thing is the absolute value of 1/2, which is 1/2, which means that the height of the graph is 1/2. And we can see that this graph has a height of 1/2. So I'm just going to write that down because that's kind of interesting. So the amplitude of this graph is the absolute value of 1/2, which is 1/2. So that's the height of this thing, and we can just see that from the graph. If we look at this graph, the one on the right, the amplitude of this one is going to be the absolute value of 3. Again, because the amplitude is the absolute value, whatever the number that's being multiplied is. And so the amplitude of this graph is the absolute value of 3, which is 3. The amplitude of this graph is the absolute value of -3, which is 3. And again, that means the height. And so the height between 1 and 4 is 3. It's not the entire height, it's the height between the low point and sort of the midpoint where it changes. Okay, it's kind of like, the other way of saying that is, it's the height of each one of these bumps. It's the height of a single one of the peaks is the amplitude. And you can see that's what's being shown on this graph. See how this A is showing the amplitude, and so it's just the height of one of the bumps. And then minus A, it would be the height of the lower bump. All right, let's take a look at the final page of this section. It's going to be the most complicated form. Okay, so it's very similar in that we have the C still, we have A still, and we still have our K, except now we are also subtracting a number inside the function. Okay, and so subtracting a number or adding a number inside the function, if you remember, is a horizontal shift. And so we still have the same definition of amplitude. You can see here its absolute value of A, right? It's the largest value the function obtains. We still have the same period, 2 pi over k, but now we have a new thing, the phase shift. And so the phase shift is what's being described here. It's how far the graph is shifted left or right. And so it's a horizontal shift of b units. And you can see that's because we're subtracting or adding b inside there. And so we do the exact same thing as we've been doing on the last page, except here is our new interval of graphing. Instead of going, so just kind of looking back to the last page, from the last page, we went from 0 to 2 pi over k. Now, we're going to go from b to b plus 2 pi over k. Okay, so everything's the same, except we just have a new interval. So everything is the same as the last page, except now we need to plug b into the period formula. So now you need to plug the value of b, which is going to be the horizontal shift, into the formula for the period. And we use b because b is going to shift the graph left or right. Okay, but everything else we think about the same. And so that's what's kind of being shown in these visual references right here. We've got the normal sine graph in blue in both of these pictures. Okay, normal sine is being shown in blue. On the left, we've got sine of x minus pi over 3. And so we're plugging in a minus pi over 3, and so this is shifting the graph to the right by pi over 3. And so you can see the red line has been shifted to the right, pi over 3. And when we add a number inside, it shifts it to the left. And so the red line in this one has been shifted to the left by pi over 3, excuse me. And so if b is positive, just as a reminder, it's a shift to the left b units. And if b is negative, it's a shift to the right b units. Just like all the other transformations, right? We're plugging in x plus or minus a number. So let's look at the first example here. So first of all, the 2 is something from a previous page. So it's a transformation of sine. Let's start there. Okay, the 2 is stretching it vertically. Okay, and then since we have an x minus pi over 3, this is a horizontal shift to the right. Right, it's literally what's going on in this picture. We've got x minus pi over 3, so it's just like what's going on in this picture. We're going to take the graph and we're going to shift it to the right. But we're also going to stretch it. So let's write down our new max and mins and all that stuff so that we can know what we're going to be graphing. So we do the max and the mins the same way. The max and min is still at c plus or minus a, so that's 0 plus or minus 2, so that's 2 and negative 2. Okay, so my max is here at 2, and my min is at negative 2. Just in case we're interested and we want to know, the amplitude of this graph is the absolute value of a, so absolute value of 2 in this case is what a is. And so in that case, we have an amplitude of 2. And again, we can see that's because the max of that graph is attained at 2. The period for this particular graph occurs from from b to 2 pi over b. And so the period itself is length 2 pi over k. K in this situation is a 1. It's like there's a 1 right here. Right, there's a 1 right inside there. And so the period of this one is just 2 pi. And so we kind of have all the general information there. Let's talk about what the period should be. So we have a phase shift. We have an x minus pi over 3 being plugged in. So this is shifting the graph to the right pi over 3. So we have a phase shift is minus pi over 3. So what we want to do is graph on the interval, like it says up here, b to b plus 2 pi over k. I know that's very strange, but the b accounts for the shifts left or right, and then the 2 pi over k accounts for the horizontal stretching or shrinking. So we're combining both of those things together. So we want to graph on the phase shift is a pi over 3. So we want to graph from b to b plus 2 pi over k. And so that's going to be from pi over 3 to pi over 3 plus 2 pi. And if we add those two together, pi over 3 plus 2 pi, that's going to be pi over 3 to 7 pi over 3. I know that's a lot of information there, but this is, it's a pretty complicated function. We've got stretching, we've got shifting, there's a lot going on. So we've got our max and our min from c plus or minus a, and now we have the period that we want to graph on from pi over 3 to 7 pi over 3. And so I know that my graph is going to start at pi over 3, and I know it's going to end at 7 pi over 3. And in the middle is going to be what's directly in the middle. So this is 1 pi over 3, and this is 7 pi over 3. And so that's a difference of 6. And so halfway between that would be adding 3 to that. And so that would be 4 pi over 3. And now we have a sine function. Right, we've got a sine function. And so we're thinking about this kind of shape, except it's on a new interval with a new max or min. And so it'll end up looking like this. And of course it goes in the other direction as well. Okay, let's finish this last one up. This last one is about as complicated as it gets. It's got all the ingredients, right? If we're looking at this formula, c plus a cosine x k times x minus b, it's got all those things in here, except it's not quite in that form. Notice how the k times x minus b is a factored form. This is not in a factored form. So the first thing we should do is write it in factored form. Let's factor a 3 out of there. And so this is going to be 1 plus cosine of 3 times x plus pi over 6. Right, because if we multiplied the 3 back through there, we'd get 3x, and then if we multiplied the 3 times pi over 6, it would be pi over 2. And so this is now in factored form, and now this is in this form that we wanted it to be, and so now we can use all these formulas that we've been using appropriately. Right, so when we look at this, we see that, when we look at this function, we see that c is 1, a is 1, because we've got a 1 out in front here, k is 3, right, the 3 is what's being multiplied on the inside, and our b is minus pi over 6. And you know, it's a minus pi over 6. I know it looks like a plus, but notice how in this formula it's negative. And so, you know, in this one, it was a negative sign, and so b was pi over 3. That's why b was positive pi over 3 on this one. But since we've got a plus here, and this is a negative in that one, we think about b as being minus pi over 6. Now we just want to write down the maxes and the mins, the amplitude, and the phase shift, and go ahead and plot. And so we see first that we've got a max and a min at 1 plus or minus 1, right? C plus or minus A. And so that's 0 and 2. And so I know this graph, the lowest it gets is 0, and the highest it gets is 2. The amplitude is the absolute value of A. And so the amplitude in this graph is absolute value of 1. Right, so let me be clear, absolute value of A, which is absolute value of 1, and so 1. So that means that the height of the graph, the height of one of the peaks is 1. The period on this one, we know we go from, we do 2 pi divided by k, right? And I'm just picking all this stuff right out from this box, right? The period is 2 pi over k, the amplitude is A, phase shift is B, and then we'll do the period as well, I mean the interval. Anyway, sorry, the period, 2 pi over k, you can see k in this example is 3, and so the period is 2 pi over 3. So what are we going to graph on? We see that we've got a pi over 6 phase shift, right? So the graph shifted to the right, and it's also scrunched in because it's being multiplied. And so we've got a phase shift of minus pi over 6, and so we want to graph on b to b plus 2 pi over k, and so that's going to be negative pi over 6 to negative pi over 6 plus 2 pi over 3. And when we add those two numbers together, we get minus pi over 6 to 3 pi over 6. Right, and 3 pi over 6 is pi over 2. And so we're going to graph from minus pi over 6, I think I lost that minus sign, from minus pi over 6 to pi over 2. And so we'll go from minus pi over 6 to 3 pi over 6, which is the same thing as pi over 2. And we have a cosine function, right? We're graphing a cosine function, and so it's going to have this shape. It's going to have this kind of shape. But we have a new max and min and a new period. And so it's going to start up here, right? It's going to cross halfway between those two at 1. So it'll do, and halfway between minus pi over 6 and pi over 2 is positive pi over 6. And so it's going to come down, let me just focus here for a second, and do this. And it would go in this direction as well, of course. All right, so I know this stuff is fairly complicated. Try to take them one step at a time, okay? Try to make sure you understand, you know, it's all based on the unit circle, guys. It's all based on the unit circle. So please understand this first page and how we translated from the unit circle to these two graphs. That's the most important thing, right? Go back through that if you need to. And then once you do that, make sure you understand each subsequent form. Start with the easiest form, Form 1. Work towards the harder form in Form 2. And then if you feel confident, we can work on and get to Form 3, which is obviously the most complicated.